Charging by induction. The third method of charging is charging by induction. Unlike conduction and friction, induction is not actual charge transfer. No electrons are moved or harmed in the charging by induction. Charging by induction starts on the same principles as all electric repulsion that we began in chemistry. Electrons don't like other electrons. Protons don't like other protons either, but they're stuck in the nucleus. They have no say about the matter. These 6 extra electrons here hate each other, they repel each other, and they want nothing better to be free of each other's company. But you know who else hates them? These 5 electrons down here. They want nothing to do with all that extra negative charge coming in from the north. They are negative enough. Thank you very much. Let's see what happens when the neutral object comes near but not touching the charged object. Protons, as we said, are stuck in the nucleus, and they too can't do anything about the turn of events one way or another. But in a conductor, such as this giant metal sphere here, charges are free to move. They can move wherever they want. Let's see what happens when we bring a neutral sphere near the charged one. It's got positives, it's got negatives, they're hanging around minding their own business. But what happens when those negatives see the other negatives on the right? They don't want anything to do with them. They hang back. They're repelled. They move away. Anytime those negatives get too close, these negative here say, we got enough problems already, and they stay away, leaving exposed positive charges on the near side over here. Check it out. We've got a near side that's completely free of negative charges with nothing but positives left, and we've got a far side where all the negatives are hanging out saying, fine, we hate each other, but we hate these guys even more. Why? Because as far as we can tell, there are more of them. Keep this in the neighborhood, and the charges will stay separated. We'll call this polarized. Polarized means it's got a positive end and a negative end. And notice that these positives are going to be attracted to these negatives. They're going to be very attractive. One of the things we saw on our first day in lab was that proximity makes a big difference. The force of attraction from the near side is probably going to be a lot bigger than the force of repulsion from the far side. Why? Because the near side is nearer. We'll come with a formula for this in a few days. We'll call it Coulomb's law. In the meantime, this appears to happen whenever this neutral object is brought near the charged one, and for as long as it's in the neighborhood. Once this neutral object is moved away, the charges are going to go about their business again. They're going to remember just how much they're repelled by each other, and they're going to rearrange. They're going to relax. They're going to chill out and go back to their original positions. This is because charging by induction is not true charge transfer. It's rearranging what you already have. See? Let's watch that again in 2D. Charge polarizes into 2 ends, a positive and a negative. Charge rearranges as soon as the outside charge is brought away. Induction is charging without touching. It's what you see when something neutral comes near something that's charged. It's not true charging. Objects polarize without transferring any net charge. They simply rearrange and then arrange themselves back when the outside charge disappears. This means the original object, our blue sphere, stays charged. It loses none of its original charge because it never touches, it never transfers. This is what we saw with our demo wands. We found that when we didn't touch, we could wave those magic wands and move those foil wings and move our lab partner's hair as much as we wanted without recharging, as long as we didn't actually touch them. However, the price we pay for being able to repeat the effect again and again is that the effect is only temporary. Everything returns to normal when the outside charge goes away. Now it makes sense to say that charge transfer is permanent in charging by conduction. When 2 objects touch, then they permanently move some of the electrons from one to the other, and there they stay. But in induction, it's just a temporary polarization that will go away just as soon as the outside charge disappears. Can induction produce a lasting effect? If we want those charges to stay where we put them and make something permanently negative or permanently positive, can we do that? Well, definitionally, no, we can't. It goes against the very definition of electrostatic induction. It's not true charging. Nothing is transferred. It's just rearranging what you already have. The electrons wish to return to their places whenever the outside charge is removed. In order to make induction permanent, we have to try to break the physics and think like an engineer. If the electrons wish to return up here to their original places, how can we prevent them from doing so? Pause the video and take a good minute or two to have a hard think-o and write down an idea. Actually, write it down. How can we prevent these electrons from going back up here? As long as you don't actually injure yourself, it's kosher. Go on. Think outside the box. To turn a cliche. Pause. Ready? Got an idea? Well, idea number 1. How about we give the electrons someplace else to go? Get rid of this jar whose sole purpose is to prevent us from doing such that, and give them someplace very attractive to run to, like a conductor where they can spread out and get away from all those other electrons. Far, far away, like the ground. Oh gosh, tons of room to spread out in the ground. I'll never have to worry about other negative charges so long as they elect to be electrons, and net charge is positive. Why? Because about half your electrons just bailed and left for greener pastures. There. We haven't lost any of the charge on our magic wand, and poof, now we have a positive demo apparatus. It didn't say that we only had to use the magic wand, it just said we had to use induction. Well, we used induction to chase all the electrons into one corner, and then we gave them someplace else to go. Alternatively, if you want the direct approach, if you want to prevent the electrons from returning, then prevent them from returning. Break the apparatus in half, and try as they may, they can't fly from here to there. Then the magic wand can be about its business. The top of your X apparatus, now broken into several pieces, will be positive. The bottom will be negative. Never said the apparatus had to live to tell the tale, but yes, we can have induction produce a lasting effect. Not a net charge. The net charge is still 0, but we've separated it into a positive object and a negative object. Engineers, gotta love them. Review. We've talked about 2 new methods of charge transfer, conduction and induction. Let's take a look at conduction. In class, we talked about the fact that conductant and conductor are not synonymous. Can conduction work on a conductor? Pause. Think. Press play. Of course it can. Conduction can work on anything. Charge a conductor, and electrons will come running from everywhere and to everywhere all over the surface. Charge it, and the whole surface will be charged. Everywhere will accept electrons and donate electrons. The whole object will be charged by touch. You will share about half the charge of the object you've been touching. What about an insulator? Can conduction work on an insulator? Pause, think, then press play. What would it look like if it did? Sure, a conductor can work on an insulator. Conduction can work on anything. In the case of the insulator, the charge isn't going to run around everywhere. It's going to stay in one general location, and one general location will be more charged than the rest. If this is the location where you are, then that's precisely what you wanted. Now, induction. Can induction work on a conductor? Sure, induction can work on anything. Induction isn't truly transferring charge, it's just polarizing. The whole surface of the conductor will polarize. All the negatives will move as far away as they can from other negatives, leaving a big region of negative charge across the bottom and a huge exposed stripe of positive charge across the top. This will attract the magic wand. You better hold on to it carefully or it'll fly right out of your hand. What about an insulator? Can induction work on an insulator? Sure, induction will work on everything. It just looks a wee little bit different. The electrons in the insulator are not free to move wherever they choose, but they are free to move within their own atoms and molecules. Nasty negative charge is coming from the north. They're negative enough already. They want none of it, so they move to the far side of their molecule. Each and every one of them moves as far as they can, leaving, again, a big stripe of negative charge across the bottom and a big stripe of positive charge exposed across the top in that general region. There's a dipole, and there's a dipole, and there's a dipole, and there's a dipole. Aren't they cute? Dipole means two ends. Each molecule has rearranged itself to have a positive end and a negative end, and all those ends are facing the same way because we've been charged by induction. You'll see here too that induction is associated with attraction, and you better keep a hold of that wand or it's liable to jump down and give those positive charges a kiss.